This is Chemistry 108, York College. Today is April 28th, 2015, and we are continuing in Chapter 7. So, after the exam, we did a bunch of kind of review and examples using quantum numbers, right? And so, if you were here, then hopefully you got a good grasp of them. If you weren't here, well, hopefully you have a good grasp of them because we're going to need to use them. So we remember N, we remember L, remember M sub L, and then M sub S, and how those can be translated into different orbital designations. So 1, 2, 3 for N, and then S, P, D corresponding to different L's, and so on. And so if we think about, does anyone recognize this equation? Yes. Who's what? Not quite. It has to do with absorbance, yeah. It has to do, we saw this in class actually, this has to do with the Bohr atom. Yes, it makes sense, but it doesn't make sense, but yeah. You're talking about the right thing, right? So we saw this with respect to the Bohr atom, right? In the Bohr atom, remember, we said this only works for hydrogen, and now we're going to kind of see why, right? So if you remember, I'll just jump back real quick to the Bohr atom. Nope, before that. Right, this does refer to, or it refers to the electronic transitions, right? And so you apply basically something quite similar in your lab, but as we'll see very shortly, that there's more to energy than just N, right? And the Bohr atom, right, assumed that the only thing that mattered was the principal quantum number, or the principal energy level, which was N. But now we see the Schrödinger wave equation gives us much more than just N. So if we were to apply the Bohr atom, then we would say, okay, so for n equals 1, or the Bohr atom formula, n equals 1, n equals 2, n equals 3, n equals 4, you can calculate what those energies are, and you can calculate the differences. And so from those differences in energy, you can get wavelengths or frequencies using E equals h nu. But it turns out that this only works for things like the hydrogen atom, or orbitals that have a single, or an atom that has a single electron. Once you get more than one electron, where the only factor is n, once you get more than one electron, you can see that the 1 is still lower than the 2, is still lower than the 3s, is still lower than the 4s in energy. But the S and the P and the D, in other words, the M sub, nope, the L, right, starts to make a difference. Right, so the angular momentum quantum number, which determines whether you're looking at an s orbital or a p orbital, has some contribution to the energy. The biggest contribution generally comes from the principal quantum number n, which refers to 1, 2, 3, or 4. But the L, SP, SPD, plays a role as well. And so the energy of the electron depends on N and L. So in general, what you're going to do, okay, so right, the slide has some review before that, right? So if we just take a step back and try to remember, a 1s, n equals 1, that corresponds to the 1, and L equals 0. L equals 0 corresponds to the s. Right, so what's n and L for 2s? N is 2. L is still 0. Right, n is 2, and s orbitals are 0. What about 2p? N is 2. L is 1. Right? L can go up to n minus 1, right? So, right, n is 2, L is 1. Yeah.
Negative 1, 0, and 1.
Negative 1, 0, and 1. Yeah, so that's m sub L. And so what about 3s? 3s is going to be n equals 3, L equals 0. 3p is going to be n equals L equals 1. And 3d is going to be? Yeah. Yes, that's what you said. N is 3, L is 2, and so on. And so what you'll notice is that as L goes up, the energy of the orbital, or the energy of the electron that would be sitting in that orbital, goes up a little bit. Right? The big jump comes from 1 to 2. A little jump comes from S to P. Yeah.
So why is it after 4s equals to 3d? Why doesn't 3d come up to 3p?
Because the gap here is sufficiently large that the 3d winds up being higher than the 4s. That's just what's observed. I mean, there's no. I mean, it's hard to put a reason on why. It just is. Yeah. Yeah.
What I was doing now is the weeks to add the 3 and the d is equal to 3, so 3 and 3 is 6, which is more than 4 plus 0.
That's a rule of thumb that you could use most of the time, but it's not really a good physical explanation. You know, it's not a good physical explanation. Right. Okay. And so let's not look at all these words here. So 1s and 2s, right, if we're comparing n equals 1 and n equals 2, I think you can kind of wrap your head around pretty easily why n equals 2 has a higher energy than n equals 1. Right? Because n equals 1, or n, the principal quantum number, describes the average distance of how far the electron is from the nucleus. Right? And so remember, the nucleus is positive, the electron is negative. In order to move from close to the nucleus to further from the nucleus, you need to increase some energy. Right? And so 2 is bigger than 1, 3 is bigger than 2. So why is 2p slightly higher than 2s? And the reason for this is kind of as follows. So we're going to introduce this a little at a time. Once you have 2p versus 2s, the implication is you already have a 1s inside 2, right? 1 is smaller, 2 is bigger. And so whatever electrons you have in the n equals 1 shell, they shield the electrons in the n equals 2 shell. What does that mean? That means they kind of block the effect of the nucleus pulling on those electrons. Right? So if I were to, try to pull on your hand, it'd be very easy because there's no one in between. But if I were to try to pull on your hand, it would be much more difficult because I would have to knock someone in the head, right? That wouldn't be so nice. So there's some shielding, right? Here's the n equals 1 subshell, and that blocks the n equals 2 shell. Now the shielding effect is less for 2s than for 2p. Why is that? Because if you look at these p orbitals, they've got these 2 giant lobes, right? And so there's actually very little of the 2p that's orbital that's contained within the size of the 1s, right? So the 2s is a sphere, right? It's not a circle. It's a solid kind of, not solid. It's a 3-dimensional sphere. So and the electron can be found anywhere inside that sphere, anywhere inside that ball. So if it could be found, your 2s electron could be found somewhere around here. And if it's found somewhere around here, there's no shielding. Right? But because the 2p has these the 2p orbitals have these 2 big lobes, they're shielded less effectively. No, they're shielded more effectively. right, because there's more 2s blocking. And so the shielding reduces the effective nuclear charge, what's felt by the electron. Right? And if it's feeling less nuclear charge, the net effect is it has higher energy. Right? It's not as stable. So 2p electrons, therefore, are going to be somewhat higher in energy than 2s electrons. And the same for d versus p, right? N equals 2 doesn't have d's, but once you get into n equals 3, remember, what do your d orbitals look like? They don't just have 2 lobes, they generally have those, 4 lobes, right? So you even have less in the middle and more on the outside. Okay. So remember, what does this all refer to, right? This all refers to the electrons within a given atom, right, or a given ion, which we'll talk about. But for now, the electrons within a given atom. And so if we think about this, right, 1s to 2s to 2p, 3s, 3p, if we're not, we learned about, exciting electrons and so on, but if we're not exciting anything, we're not putting in any energy, any additional energy, the electrons are going to want to go where they're the most stable, and they're the most stable where they have the lowest energy, right? So if you have an atom with 1 electron, where is that 1 electron going to want to live? It's going to want to live down here, right, 1s. Remember, how many electrons can fit in each orbital? 2, right, a plus and a plus 1/2 and a minus 1/2. And so if you're helium and you have 2 electrons, where are those electrons going to want to live? Also in the 1s. Once you get to lithium, right, lithium has, as an atom, has 3 electrons. The first 2 are going to want to live here, then you're out of space here, right? And so the third one is going to want to live 2s. And so what happens is that what's called the building up, or the Aufbau principle from the German for building up, the electrons fill up from lower energy to higher energy. And so that's going to be the first, that's going to be the second, right? And this is typically how we would draw them, right? This would be the plus 1/2, m sub s equals plus 1/2, m sub s equals minus 1/2. And then you're going to go dot, 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 right? And so this is, okay, so let's take a step back, right? So boron, right? Boron has an atomic number of 5, so it's going to have 5 electrons, right? As long as it's an atom. And so we're going to go 1, 2, 3, 4, 5. And up to now, it's pretty straightforward. But then what happens? And then you have 3 orbitals that have the same energy here. So once we get to carbon, which has 6 electrons, where is the next electron going to go? Is it going to go into the same orbital, or is it going to go into the next one? And it turns out that it's going to go, into the next one. And so there's another principle or rule here called Hund's rule. The most stable, or lowest energy, arrangement of electrons in subshells is the one with the greatest number of what we're calling parallel spins, or the greatest numbers of equivalent m sub s values. So this is m sub s plus, this is m sub s plus, plus 1/2 and plus 1/2. And so another way of saying that is they have parallel spins, right? There's 2 points here, right? One is it goes into the next orbital, the next orbital in the 2p subshell. The other point is that it's in the same direction, right? So it's not up here and down here. It's not up here and down here. It's up and up. And so it turns out that having these parallel spins is energetically favorable. It's stable. So if we go from C to N, right, N has 7 electrons, where's the next one going to go? It's going to go in the third shell, and it's going to be pointing up or down? Pointing up. Oh, before we get there, well, it's going to be pointing up. Okay, I don't have that on the slide.
If you have like 8 electrons, is it going to start pointing down or is it going to jump to 3s?
It's going to start pointing down, right, because it's going to fill the subshell first before it goes to the next one. There's a couple of exceptions to that, and we'll talk about why. But in general, that's what's going to happen. So here we have an abbreviated way of expressing how the orbitals are filled. For carbon in the ground state, you're going to have 1s, and the 1s has 2 electrons. You're going to have your 2s, and the 2s has 2 electrons. And you're going to have your 2p, the 2p has 2 electrons. So we could abbreviate that 1s2, 2s2, 2p2. This is a slide that, or this is a diagram that books like to say. I'm not crazy about it because, we almost never get all the way down here. So if we start from the top, right, this is how we fill, right? 1s, 2s, 2p, and then from 2p it goes to 3s. From 3s it goes to 3p, right? And then there's this point that the 4s is actually slightly lower in energy than the 3d, right? So the 4s, just based on what we observe, is slightly lower in energy than the 3d. So the 4s fills next, and then the 3d. Right, 4s, 3d, 4p, and then the same thing. 5s is lower than the 4d, and then the 5p, and then the 6s. We rarely ever get past that when we're asked to fill in, states. But you can use, if you really like to, you can kind of put this in your head. But otherwise, this kind of diagram here should make sense, right? 1s, 2s, 2p, 3s, 3p. Then it goes to 4s, 3d, 4p, right? And then 5s. And so, in other words, once you get to d orbitals, you fill the next s before you get to the d. Right? So 3p doesn't go to 3d, it goes to 4s. 4s, after 4p, it doesn't go to 4d, it goes to 5s. Yeah, so F, once you get to F's, you may start thinking about this, right? So from 4d, so you're going to go from 5s, and then you're going to fill in your 4ds, and then you're going to finish your p's, your 5p's, right? So you're going to get your 5s and 5p all done. And before you move to 5d, you're going to go to 6s. That's kind of the same pattern, right? But once you have n equals 4, you have f orbitals. So before you even get to the 5d, you're going to get to the 4f. Between 4f, 5d, and 6p. Once the 6p is done, you're going to go to 7s. Right? Once you go to 7s, you're going to go back to the f, 5f, then back to the 6d, then to the 7p. So it's good to understand. On an exam, I wouldn't probably not ask you to fill in something that long just because it takes a lot of time and that kind of thing. And also, once you get down into the F region, you get a lot of exceptions that we're not really going to commit to memory. So the electron configuration is how the electrons are distributed among the various atomic orbitals in an atom. So we said, we kind of showed this for the carbon, but first you have the principal quantum number, 1, and then the letter that corresponds to the angular momentum quantum number, or the subshell, and then the number of electrons in that orbital. And so the electron configuration, we would say, is this kind of shorthand. The orbital diagram is if we wanted to draw the whole thing out, right, from bottom up. So for hydrogen, it's going to be that, and so on. Okay, so we'll, before we get there, we'll do an example. Or we'll do another example. So let's do it backwards. So draw an orbital diagram and write the electron configuration for magnesium. And so let's do this one together, right? So magnesium has how many electrons? Magnesium metal. How many? 12, right? So magnesium has an atomic number of 12, so it has 12 electrons. Remember we said this is the shorthand for electrons, E minus. And so let's draw our orbital diagram. You can draw boxes, you can draw lines. So there's 3 and 2p, and then we have our 3s, and then we're going to have our 3p. And I don't know if we're going to have to go past that, but if we do, we'll do it. So what are we going to do? We're going to fill in from the bottom up, right? So we're going to say 1, 2, 3, 4, 5. Where does the next one go? Up. 6, 7. No, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 8, 9, 10, 11, 12. So we actually don't need our 3p. And this is going to be 1s, 2, 2s, 2, 2p, 6, 3s, 2. Questions here? Okay, so there's a concept here that we should introduce. So there's, in general, 2 types of magnetism. These are not the magnetism you see for the magnets that stick on your refrigerator. These are substantially weaker. Paramagnetic compounds or paramagnetic species, they're attracted by a magnetic field, and they have unpaired, and those arise from species that have unpaired electrons. And so if you had something like that, it'd be paramagnetic. The opposite is diamagnetic. They're repelled by a magnetic field, and diamagnetic, all electrons are going to be paired. Right, so the magnesium is paramagnetic or diamagnetic? It's diamagnetic, right, because all the electrons are paired. In other words, each orbital has pairs of electrons, right? There's nothing unpaired like this. Okay, so let's do the same thing, except for, yep, what? Sorry? Oh. It's the same thing as, except for sulfur. And let's ask also, is it para or diamagnetic? Okay, so put your heads together gently and do it. Maybe start a little lower. Yeah, just because you might run out of space. Okay, so not bad. Count your electrons. How many electrons should you have? 16. Wait, let her figure it out herself. Good. Okay, so this is right? So it'd be probably a little easier if you made the spaces kind of bigger and kind of like this, but this is not wrong, right? So you got your 1s and your 2s and your 2p, then your 3s and your 3p. And we have 16 electrons. Sulfur has 16, right? So you'll notice that these are parallel, right, and in different orbitals. And we have it right, 1s2, 2s2, 2p6, 3s2, 3p4. And so is it diamagnetic or paramagnetic? It's paramagnetic, right? Okay, so I want to do one more here, right? So let's do neon. So neon has how many? 10? 10, right? 1s, 2s, 2p, and I think that's all we're going to need. So we're going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What this is, you can see here's your n equals 2 shell. And it's entirely full. Right? So you have 2, 4, 6, 8 electrons. And then you have nothing else. Right? And so this is what we would say, this is what we would call a closed shell. It turns out that this kind of closed shell configuration is quite stable. And so one abbreviation that or one way that these electron configurations are often abbreviated is to say, in the case of magnesium here, well, we have, right, the closed 1 shell, closed 2 shell. Right? This shell is not closed. So what we can do is say, okay, all of this is identical to this, right, for neon, 1s2, 2s2, 2p6. And so we're going to use the closed shell of neon and then add to it our 3s2. And so for this one, we could add our closed shell of neon and add 3s2, 3p4. So that's going to be your kind of abbreviated electron configuration. And as it turns out, if you use a little bit of sort of reasoning, these noble gases are all going to have this kind of closed shell configuration. So we can use essentially the nearest or the next lowest noble gas to kind of say, okay, I don't want to write out 1s2, 2sp, 2s2, 2p6 over and over. I can just write neon. Right? And so let's try potassium. And let's do it with, and write the abbreviated electron configuration. You don't need to write the 10. Yeah, the 10 is implied. Yeah. Yep.
After the argon, then it's 4s, right?
Yeah. So in this case, we're not asking you to write out the whole orbital diagram, just the abbreviated electron configuration. And so we're going to go over to potassium, and we're going to say potassium, the next lowest is noble gas is argon. Right? So we're going to have argon, and then we're going to have one more electron. And it is going to be 4s1. Let's take a look at the periodic table. It has a very interesting shape, right? It has kind of this tall block here, and this tall block here, and this sort of low, wide block here, and then this really low, really wide block here. It's steps, right? The energy is quantized here. So I can't reach this, but these elements here are going to be filling in their s orbitals, right? So you're going to be, everything here is going to have something s1. Everything here is going to have something s2. Here it's going to be p1, p2, p3, p4, p5, p6. That much is basically always true. Now this is called so this is the S block and this is the P block. This is called the D block. And you're going to be filling in your d orbitals. In the case of the d orbitals, there are some exceptions, or there are some strange, it's kind of unpredictable. I would say in some cases they're very predictable. In other cases, you really have to do, there's no real intuitive rule. You just have to do the calculation or make the observation. But in general, you're going to be filling in your d orbitals from left to right, from 1 to 10. And so, and then this is your F block, right? So these guys are kind of from here, from lanthanum to lutetium, they're kind of jammed all in here, right? If this wall was really wide, we could shift the S block all the way over and stuff the F block in here, right? So the lanthanides over here and the actinides over here, but we don't, right? Because it's more efficient space-wise to do it this way. Okay, so let's start. Okay, so we did this one, we did that, we did, and so that essentially corresponds to this. All right, so here's your S block, your P block, your D block, and your F block. And hydrogen, 1s, right? And the helium is the only exception, right? I didn't know helium was so offensive. So helium, in some periodic tables, you'll see helium, no, sorry. Well, anyway, helium goes with the noble gases, right, because it is a noble gas that has a closed shell, but helium also is filling in its s orbital. Besides that, you have your 2s, 3s, 4s, 5s, 6s, 7s, right, 2p, 3p. And remember, your 3s, your Ds don't start until 3, and they come when? Or they start filling when? They start filling after 4s, right? And when do your Ds? They start filling after 5s. And 6s goes to 4f, goes to 5d, goes to 6p. 7s goes to 5f, goes to 6d, goes to 7p. Right? And so this periodic table reflects that kind of diagonal pointy arrow slide about 3 or 4 slides ago. Let's do, what should we do first? Okay, so let's look over here. This is not something you really need to memorize because most of the time you can build it. Right, here's your heliums, right? So this is your second row from lithium to neon. Here's your third row from sodium to argon. And then your fourth row starts potassium and just kidding. Okay. So we lost part of our table here. Okay, so let's take a look. That's okay, because the potassium and the calcium are kind of straightforward. I want to point out something here. Okay, so if we look over here from 39, or from 38, right? So 38 is strontium, is down here. Right, 39 is the deuterium. And so strontium is krypton and then 5s1, 38. Then 39 is 5s1, 4d1. That makes perfect sense, right? Then zirconium, 40, is 5s2, 4d2. Then notice what happens here. The niobium, Nb, is not 5s2, 4d3. It's actually 5s1, 4d4. Can anybody give or try to explain why that might be? Sorry? Right, so niobium is Nb, niobium. The abbreviated electron configuration is Kr, and then 5s2, nope, 5s1, 4d4. Right, what it's not is krypton 5s2, 4d3. That's kind of what we might expect based on just the Aufbau principle, right, building up. Right, versus this. And this is the one that's generally, that's observed. So if we draw, okay, so we're not going to draw our core. We're just going to say we have krypton here right now. Then we have our 5s and our 4d, right? Our 4d has 5 orbitals, right? So we got 5s1, 4d4. So 1, 2, 3, 4. Yeah, so I'm telling you that that's what we would expect, but that's not actually what happens. Yeah, it's actually 5s1, 4d4. What did I tell you before about spins? Right, so having parallel spins is a stabilizing force, right, a stabilizing factor. So what this enables you to do is get more parallel spin here. right, in the 5s1 and 4d4. So 5s2, 4d3 would have left us like this, right, only 3 parallel spins. 5s1, 4d4 gives us 5 parallel spins. So because these are so close in energy, having more parallel spins actually is favorable. Say that again?
How many exceptions are there for the 5s and then
Okay, so if you look here, so we go from 5s1, 4d4, 5s1, 4d5. And so the niobium and the molybdenum are exceptions. And then we go from 5s1, 4d7, 5s1, 4d8, and then it goes straight to 4d10, right? 5s1, 4d10, 5s2, 4d10. These go straight to 4d10 without filling up the 5s first, because having a closed subshell is very favorable. All right, and so there's lots of exceptions if you want to, kind of look through them. There's 2 exceptions that we're going to have to remember. That is, and so this is the explanation, right? And they all have to do either with parallel spins or closed shells, right? So the ones we have to remember are this family over here, Cr, Mo, and W, right? So chromium, molybdenum, and tungsten. So for chromium, molybdenum, and tungsten, they're always going to be, let's say this, Nd5, N-1, S1. Right? So that's going to have your noble gas core plus 1, 2, 3, 4, 5. And that's because, why do you have to remember this? That's because it always happens for the whole family. In some cases, in some of these cases, like the niobium, I think the niobium occurs, but if I remember correctly, the vanadium doesn't. Right? The vanadium is in the order you expect. So I don't expect you to remember all of the exceptions and when they occur, but when they happen all the time, I expect you to remember it. So that's the one group of exceptions. And the other group of exceptions is over here, copper, silver, and gold. Right? Those are your precious metals. Right? So copper, silver, and gold are going to be N-1, S1, and then Nd10. And that's going to give you a closed subshell. And so this one you can view it 2 different ways. One is you have, well, let's look at it this way. You have maximum parallel spins. And so these are the 2 groups of exceptions that we'll have to remember, right? So instead of going like 4s2, 5d4, we go s1 and d5. Instead of going s2, d9, it goes s1, d10. This is fun, right? Let's do another one. Because we're on a roll here. let's try now we have a charge. So it loses an electron. So sodium starts with 11, and then so we would, yeah. So draw the orbital diagram. And then let's do another one that's, let's say, and let's do one more that's okay, who wants to do these on the board? Let's be brave enough to do them. No, just one. Just one. Sure. Okay, here you go. Who wants to do the second one? Okay. Who wants to do the third one? Here you go. Yeah? Okay, there's a chalk right in front of you. So let's draw them in energy order so you can see the low to high. For yours, it's kind of especially important. Yeah, good. Okay, so very good. So we've got our sodium, right? Sodium has an atomic number of 11, so it has as an atom 11 electrons, right? But it's a plus 1. Plus 1 you get by losing 1 electron. So we're going to have 10 electrons. And we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's good. Phosphorus is 15, right? And then minus 3, how do you get a minus 3? You add 3 electrons, it's going to be 18. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's happy also. I meant that. Titanium is 22, right? So titanium is 22, and how do we get a plus 2? You take away 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That looks happy, right? But it's actually not. So if we were to draw out titanium the whole way, it would be, and then 3D, right? And we'd have 1, 2. And when we have plus 2, we take away 2 electrons. Now it turns out when you have 3 d orbitals, or when you have d orbitals, the first electrons to come out are actually from the S right before your d. right? And so that's because they come out from the orbitals with the highest n first. And so I tricked you. that was actually a trick question, but I think you can handle it, right? So that's you'll get. I'll give you a cookie next time or something. So this is going to be your Ti2+. Now let's do one more before our break, and put your heads together.
Wait, so for titanium,
Yeah.
then when I write up this electronic configuration, do I just skip 4s entirely?
It's going to be 1s2, 2s2, 2p6, 3s2, 3p6. If you want to put in 4s0, you can. You don't have to.
But isn't it a 4s before D?
Yeah, so yeah, we can 4s0 and then 3d2. And so let's try Fe3+. Now put your heads together and do it. Right, so Fe3+ or Fe has 26 electrons, right? So the atomic number equals 26. Right, so the atom is going to have 26 electrons. The 3+ ion is going to have 23 electrons. So this has 23 electrons. What I'm going to do is I'm going to draw out the 26 first and then take away 3. So 1s, 2s, and where am I going to have to end, just based on its location in the periodic table? That wasn't a hypothetical question. Where am I going to have to end based on 3D? Very good. So I'm going to have 23, and I'm going to start with 26. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, so now I'm going to take away 3. The first 2 come from the 4s. So 26, 25, 24, and then 1 is going to have to come out of the 3D. Which one is going to come out of the 3D? The one that's doubled. So there you have it. It's going to be one, well, we'll do it abbreviated. So the one before iron is argon, right? So argon, and then 4s0, 3d5. Let's take a break. The first thing that we're going to learn about is valence electrons, right? So we've almost had this concept in our head, almost, right? But valence electrons are electrons that are in the highest shell, or the highest n, that have the highest n. In other words, because n indicates average, there's an echo here, because that's cool. N indicates the average distance from the nucleus. So the highest shell, or the valence shell, those electrons are furthest away from the nucleus. And because they're furthest away from the nucleus, they're closest to the outside world, to the rest of the world. And because they're closest to the rest of the world, they do a lot of the interesting chemistry that has to do with interacting with other molecules and other atoms and that kind of thing. So having the valence shell filled is energetically favorable. That's a good thing. Right, so therefore, we learned this. Atoms tend to gain or lose electrons, right, to form ions, until what we said before is until they resemble the nearest noble gas. So chlorine tends to gain 1 electron, so it resembles argon. From the point of view of electrons and quantum theory and orbitals, the reason for that is if chlorine gains 1 electron, it has a closed shell, right? It has a filled valence shell. This tends to be known as the octet rule, right? Because if you have a filled S and a filled P, in any case, you have 2 plus 6, right? 8 electrons. Metals lose electrons, nonmetals gain electrons. Sometimes they share electrons. This is setting the stage for bonding, which is going to be in chapter 9. And then full subshells, half full shells are also energetically favorable, but not as much as a full shell. So let's take the opposite look. So we have our valence electrons. Those are the outermost electrons. Everything that's not a valence electron is called a core electron. The interior electrons, where n is not the, if the highest n for that atom is 5, the core electrons would be all the electrons that have n equals to from 1 to 4. And we introduced the concept of shielding in the last chapter. It was a little bit hard to understand. Go back and look at the slide for that particular application of shielding when we're looking at kind of S versus P versus D. But when we're looking at interior or core versus valence, the shielding concept, I think, is much more straightforward. So the interior or core electrons shield the valence electrons from the nuclear charge. Right? So that is that is all the electrons that aren't valence electrons are kind of between the valence electrons and the nucleus, right? And because of that, they're kind of blocking the nuclear charge. So there's this quantity called Z effective. Z, as you move on in chemistry, you'll see tends to be an abbreviation for nuclear charge. Z effective is what we call the effective nuclear charge, or the amount of nuclear charge that an electron kind of feels. So how does Z differ from Z effective? Well, Z effective is influenced by the amount of shielding. So the more shielding you have per electron, the lower the Z effective. Right? So more shielding means you have less, the electron's feeling less nuclear charge, it's feeling less pull, and so the Z effective goes down. So let's start with the easiest concept, right? Because periodic trends has to do with the periodic table. As you go from small to big in a column, right, in a family, the shielding increases. The reason for that is you get more levels of n. We're talking about the valence electrons, right? Because you're getting more and more and more core electrons, right? If you look at beryllium, the only core electrons in beryllium are from n equals 1, right? But when you consider magnesium, the core electrons for magnesium are from n equals 2 and n equals 1. And when you look at calcium, the core electrons are from n equals 3 and 2 and 1. So as you go down a family, the shielding increases. As the shielding increases, what happens to the effective nuclear charge? It decreases. Right? So as you go down a family, the shielding increases and the effective nuclear charge felt by the valence electrons decreases. So the effective nuclear charge felt by strontium valence electrons is going to be lower than the effective nuclear charge felt by the calcium, which is lower than the magnesium, and so on. So as you go down a column, that kind of is intuitive, makes sense. Now as you go across a row from left to right, the shielding decreases. Or let's put it this way. The shielding per valence electron decreases. So if we were to go from lithium to, so what's that saying is as we go from lithium to beryllium to boron to carbon and all the way across, the shielding of the valence electrons by the core electrons gets weaker. So we think about it this way. If we look at lithium, lithium has how many valence electrons? 1. Right? It has 3 electrons, but 2 of them are core electrons, n equals 1, and 1 of them is a valence electron. Right? That's the 2s electron. So lithium has 1 valence electron. Neon has how many valence electrons? 8. Yeah, 8, right? Because neon is 1s2, 2s2, 2p6. So all of the n equals 2 electrons, a 2s plus a 2p, are the valence electrons. And so how many core electrons does lithium have? 2. How many core electrons does neon have? Also 2, right? The n equals 1 electrons. Those are the core electrons. So if you think about lithium, it has 1 valence electron being blocked by 2 core electrons. If you think about the neon, there's 8 valence electrons being blocked by the same 2 core electrons. In which case is the blocking or the shielding going to be more effective? When it's for lithium, because right, because right, for lithium you have 1s2, 2s1, right? This is lithium. Neon, you have 1s2, 2s2, 2p6. Right? So here you have 8 valence electrons. Here you have 1 valence electron. So here you have 2 electrons blocking a single valence electron. That's going to be pretty effective. Here you have the same 2 core electrons blocking 8 valence electrons. Much easier for 2 to block 1 than it is for 2 to block 8. Right? So as you go from left to right, the shielding gets weaker, or there's less shielding. Right? So shielding decreases as you go from left to right, and if shielding decreases, the effective nuclear charge increases. That makes a difference. That makes a difference in basically all the stuff we're going to talk about next. So atomic radius. Radius is the size for either like a circle or a sphere, is from the middle to the outer edge. Right? Atomic radius is basically saying how large the atom is. And the radius increases as you go from low to high, right? As you go from up high to low, right? Low molecular weight, high molecular weight. From the top of the family to the bottom of the family. And that's because n increases, right? As n increases, your outermost electrons get further away. Now, what about it as you go from left to right? As you go from left to right, n is the same. So the distance, in principle, is about the same. But we have to think now about z effective. In the last slide, we said as we went from left to right, shielding decreases, and z effective increases. So if z effective increases from left to right, that means the effective nuclear charge felt by the valence electron increases. That means they're being pulled harder. If they're being pulled harder, what's going to happen to their distance? It's going to get smaller. They're going to come closer. Right? So the radius decreases from left to right across a row because the effective increases. The electrons are pulled closer.
Wait, but didn't the effective decrease from left to right?
Shielding decreased it from left to right, so the effective nuclear charge increased. Right? Because as you go from left to right, you get more electrons that need to be blocked by the same, more valence electrons that need to be blocked by the same core electrons. So the shielding decreases. If the shielding decreases, the effective nuclear charge increases. And so the electrons are pulled closer. And so here's an example of atomic radius, or here's sort of an image. As you go from left to right, and these are in picometers maybe. As you go from left to right, you can see the sizes get smaller. As you go from left to right, the sizes get smaller. As you go from top to up high to down low, from top to bottom, the sizes get bigger. Right? So where would you expect the biggest atoms to be? Bottom left, right? And the smallest ones you would expect to be top right. Here's another trend, one that we call ionic radius. Ionic radius is very similar to atomic radius, except instead of looking at the atom, we're looking at the ion, the charged group. Now, as we go down a family, again, from top to bottom, N is increasing, right? For example, lithium, sodium, these guys all form a +1 ion. And so we're comparing +1s to +1s, but the valence N gets bigger. So the ion gets bigger. Within a row, now the effect is more complicated. So if you are a metal, like sodium, what's going to happen to you when you form an ion? You're going to become a positive charge, so that means you gain or lose an electron. You lose an electron. So if you're sodium and you have 11 protons and 10 electrons, right? So you have 11, if you're sodium and you have 11 protons and 10 electrons, you have more plus than you have minus, right? So what's going to happen to your electrons? They're going to be pulled closer, right? As an atom, you have 11 and 11, right? And so there's a particular size there. Now you decrease the number of electrons. When you decrease the number of electrons, you're going to be pulled closer, right? Because you have more plus pulling on the minus. So the minuses that were out here, now you can pull in here. So positive ions are going to get smaller, and the more positive they are, that is, the smaller they're going to get. So that means +2s are going to be smaller than +1s. +3s are going to be smaller than +2s. If we're looking at negatives, anions, the opposite effect occurs. So let's take a look at fluorine. Right? Fluorine as an atom is about 9 and 9, right? So it's 9 plus and 9 minus. When fluorine becomes an ion, it becomes -1, right? So you gain an electron, becomes 10 minus. So from 9 plus and 10 minus, you have more minus now than plus. So what's going to happen to the minus? The minuses are going to repel each other. They're not going to be, there's not enough plus to pull them in, so the size is going to get bigger. And so for the more negative charge you have, the bigger the ions are going to be. So the trend looks something like this, right? We're going to ignore the transition elements because it's kind of complicated. But as you go down for the main group elements, which is the S block and the P block, this is what's going to happen, right? You're going to go, for your cations, you're going to get kind of, your biggest is going to be in group 1, and the next is going to be in group 2, and then your next is going to be in group 3, right? Group 4, you'll notice is not here because at least they're not all here. Group 4 tends not to form ions, right? Carbon, we don't really think about carbon plus, carbon minus that much. And once we get to group 5, nitrogen is ±3, right? Oxygen is -2, fluorine is -1. So the general trend is big to small, right? Big on the left, small on the right, except you have to separate your cations from your anions. So your biggest ones are going to be your leftmost, most negative charged anions, and then you're going to go to your cations, and they're going to get smaller as the positive charge increases. So in other words, the more negative, the bigger. The more positive, the smaller. One more that we're going to try to start here anyway, and this is ionization energy. Ionization energy is the amount of energy you need to remove an electron. Right, so higher ionization energy means that you need more energy to remove an electron, right? And so the electron is more tightly held. The first ionization energy refers to the energy needed to remove the first electron. The second ionization energy refers to moving the second electron, and so on. And so what does that mean? That means if you have a low ionization energy, it's going to be easy to remove an electron. What kind of elements are those? Yeah, so sodium, potassium, in general, metals, and in particular, the group 1 metals, right? it's going to be easier to move one electron. What type of elements is it going to be hard to move an electron from?
Oh no, towards nonmetals, right?
Nonmetals, specific, particular. Yeah. So things like chlorine, noble gases, and so on.
The halogen.
Yep. So you basically got it here, right? For the first ionization energy, okay, we'll get to the down a family, but across a period, the first ionization energy increases, right? Because the very simplistic view, it gets more complicated, but the very simplistic view is that metals, it's easy for metals on the left to lose electrons. It's hard for nonmetals on the right to lose electrons. There's some exceptions we'll talk about next time. But before we do that, the ionization energy as you go from top to bottom decreases. And that has to do with the shielding and the effective nuclear charge. Right, so remember, as you go from top to bottom in a family, what happens to the shielding? Shielding increases. The effective nuclear charge decreases. So if the effective nuclear charge on the valence electron decreases, what does that mean? It means it's easier to get rid of an electron. It's not being held as tight because the effective nuclear charge that's pulling on it is not as big. So ionization energy increases down a family, but increases in general across a period with some exceptions that we'll talk about. So where would you expect to find the element that's, or which element in the periodic table do you think it would be easiest for that element to form a plus one ion? Which element has the lowest first ionization energy?
Lithium.
Because it gets lower as you go down a family. So it's going to be down here, like francium probably, cesium, francium. Okay, so we'll stop here. I'll give back your tests. And bring your sheet to class next time.